The first speaker of the day is going to be Ivo Dell'Ambrogio, and I'm not sure whether he qualifies as a guest or as an Italian speaker. That's hard to tell. But today we have Ivo Dell'Ambrogio. He's going to talk us about Mackey 2 functors. And Ivo, when you feel ready, you can take the stage.
Thank you, Ivan. Thank you to all the organizers. I think I am a guest because I am not Italian, and I'm not a category theorist. Category theory is whatever the mathematical equivalent of a mother tongue is. Certainly, category theory is for me. And although I don't think I've ever proved any result in category theory in my life, but I used it a lot. And so I'm really honored to open, I think, the first talk of this year's Ithaca Fest. And I think it's an awesome concept. I really like this idea. I like what you've done with it, the execution, the people in it. Everything is very awesome. So congratulations for setting this up. I think it's a really good idea. I will talk today, so maybe I will share my screen so you can see the title. Let's see if I can find it again. All right. So the title is Mackey 2 functors, or as I've amended it, an introduction to Mackey 2 functors. I will give an introduction only because, although very young, it's exploding, this theory, because apparently it's very, very general. So I'm going to show you first maybe a list of references that exist already. So this is mostly a collaboration that I'm doing with Paul Balmer at UCLA. We have a book that came out last year where we introduced this notion of Mackey 2 functors, and what I will explain, Mackey 2 motifs also. And then we have a couple of articles. One just a couple of weeks ago appeared in Mathematische Annalen, so it was accepted, sorry. Then we have another preprint, and then I mentioned here the preprint of my current PhD student, because I really like his result, and I think it's a good example of the kind of applications you can have of this theory. So these are the references that exist at the moment, and there are many more in preparation. So what can we say about this? Well, I will start with a question, because we are all, we like philosophical questions, I suppose, in this crowd. So what is representation theory? So whatever your favorite answer, whatever your leanings, groups acting on vector spaces, okay? Then you can shoot out on a tangent and do, I don't know, some kind of infinite groups, topological groups, acting, like on unitary representations on Hilbert spaces, whatever. You can do Hopf algebras, Hopf algebroids. You can look at general, functors as being representations, whatever you want. But this is the core historically. And so I will warn you, I will not leave this core during this talk. I will only introduce techniques which apply for finite groups acting maybe not on vector spaces, but in some kind of additive or linear way. But the techniques will become more and more categorical, so you will see. So basically, what is this about? Well, we have a finite group G, we fix a field of coefficients K, and then we study the category of KG modules, say left KG modules, let's say finitely generated, if you want to be very concrete and down to earth and even classical, I must say. And then linear maps, KG linear maps, between them, they form a category. So we want to study this category, right? And from the start, you encounter the classical dichotomy in this subject, where on the one hand, you have the semi-simple case, meaning that if the characteristic of the field does not divide the order of the group, for instance, if the characteristic is 0, so complex representations, rational representations, then Maschke's theorem tells you that every finite dimensional representation is, in a unique way, a direct sum of simple ones. So in the end, you don't really need a category theory. It's enough to study the representation ring, which is, at least here, the K0 group, K0 ring of your category, but this ring contains the whole information basically. So that's it. Historically, you do character theory first, but then there is the other case, namely when the characteristic of the field does divide the order of the group. That's when interesting stuff really starts to happen. And why? Because, well, now we have an abelian category mod KG, which has non-trivial extensions. So you can start to, to study which indecomposable representations extend which others and so on. They're not all simple. So you need categorical and especially homological tools. So people have introduced, group cohomology, Tate cohomology, all that kind of stuff, homological algebra methods. So I will represent them here, if you want, by the derived category of the module category, and also the stable module category, which is both are triangulated categories. So you can do homological algebra in it. You can study group cohomology, Tate cohomology, that kind of stuff in relation to representation theory. And they are, I would say, the focus of people who do modular representation theory of finite groups. They are interested in the structure and properties of these categories, which contain the module category, of course, at least the derived one, but they are much richer in structure. So, all right, what do? We have three categories. We want to understand them, but it's not just categories. So there is an extra layer which has always been used, and it consists of a two-categorical structure. Now, from now on, I will call M of G either one of these three categories of interest to representation theorists: the module category, the bounded derived category, or the stable module category. I will not define it. It's, if you don't know what it is, it's some kind of, you take, well, I'll define it. It's just take finitely generated modules as an additive category, and you kill all the maps that factor through some projective module. So for example, in the semi-simple case, nothing is left. But in the modular case, you are left with exactly what is interesting in the modular case. And moreover, the category becomes triangulated by some magic. So you can do homological algebra, you find cohomology and so on inside. Well, so now we have these categories that depend on G. Let's call them M of G. So we can vary G and see what happens. That's what representation theorists like to do, right? And there are these basic tools which are used all the time. Namely, first of all, we have these functors relating the categories M of G for different groups G. We have restriction functors, induction functors, and conjugation functors. So if H is a subgroup of G, we can restrict our representations or complexes of representations. We can induce them back up, right? And then also, if we have an element of the bigger group, we can conjugate the subgroup, and there is a conjugation functor which shifts the action on the representation. You can recompose with the conjugation on H, and you get an action of the. So this is just a notation for the conjugated subgroup by the element G. I think it's very standard. So we have these functors relating the categories, right? There are others, but these are the most basic ones, of course. And then you have to notice that these functors are not any random functors, they are adjoint. So the induction functor is the left adjoint to restriction, and in fact, it's also right adjoint. And I must say, this is why I'm restricting attention to finite groups here. More complicated things like algebraic groups, you might have different adjoints. You always construct, left and right kind of extensions, but they might not be isomorphic. So if I want this ambijunction here, this Frobenius adjunction, then we want to at least have finite index between H and G. So we'll just take finite groups for simplicity. And I must also have additive categories. This is something else I want to stress. If you take, say, finite G sets, H G sets, you can restrict the G action to an H action, you have two adjoints, kind of extensions. They're not isomorphic by any stretch of the imagination. So in some sense, you can, in the examples at least, you see that as soon as your categories are additive and your functors are additive, this finite index suffices to have this ambijunction here. It's actually a theorem, but I don't want to give you too many details. What else can we use here? Well, people always use also some natural isomorphisms given by conjugation. So conjugation appears again, but now as a natural isomorphism. For example, like this. So you can restrict from G to H, but you can restrict to G from G to some conjugate of H. And then you can move down here and conjugate back to GH, or you can restrict directly. This triangle does not commute, but it does up to some specific isomorphism given by the element G again, which this might seem some kind of pedantry, like, okay, the functors are isomorphic, so they're the same. But, you know, when formulas get complicated, you need to track your isomorphisms, your natural isomorphisms. You cannot just throw away these subtleties. You have to keep all this information. It can become pretty tricky. So let's just notice that it exists for now, and it's used all the time. And then you have something else, this ingredient that will give the name to our theory. It's called the Maki formula. This is now for, if you have two subgroups, K and L of G. So this looks awful. If you've never seen this, you might say, what? This is just ugly. It is. So I will make it less ugly in a moment. I will replace it with something much more canonical and beautiful and categorical. But this is the form that's always encountered in textbooks. Maybe not even as an isomorphism of functors, but as an equality between some maps. Small picture. So you have L as a group of G, K as a group of G. So you can induce up from L and then restrict to K, right? You can induce up from K to L, from K to G, and then restrict from G to L, okay? Like this. But this isomorphism says that you can also go down in the intersection of subgroups of, so you intersect K and L, but you also have to conjugate by all the possible elements of G. And if you do it in all the possible ways, then it's the same. You can go down and back up. And if you sum up all these functors, you get the same as going up, right? So it means that you can always reduce this kind of traffic to smaller subgroups. So you can do like induction arguments and so on. So you can imagine why it's very useful, although it's a really ugly formula, okay? All right, so this is higher categorical structure that has been used for decades, even without really saying what it is. So, well, let's make it better. Let's axiomatize it first, right? Let's introduce some better formalism for all this. I will use this notation, groupoid F, GPD F, for the two category of finite groupoids, faithful functors between them, and natural isomorphisms. So that's a very nice two category. And I will only take faithful functors between groupoids just to simplify, but I could take a variance here. That's not important. That's the simplest situation. And then I also need the two category add of all additive categories, additive functors, and natural transformations between these functors, so that I can express what is a Mackey 2 functor. So the definition is very young, okay? It appears in that book from last year, but of course there is not much original here. If you look at what I'm going to write now, you'll recognize everything I write. But nobody has really exploited this definition before or written it down in these details. So we fill the gap here, okay? We are profiting from the laziness of representation theorists who have never really exploited this systematically. So a Mackey 2 functor is a 2 functor from groupoid with faithful morphisms into additive categories. It's contravariant, okay, because you have to understand it like this. If you have a H in G, for example, a subgroup inclusion, okay, and you have some category, some additive category for G, another one for H, and then I want the functor associated to I to be some kind of restriction functor, okay, it goes the other way. I will write it as, and then isomorphisms of functors of groupoids will give isomorphisms on the right, and it's two functorial, okay? So nothing very fancy so far for category theorists, I mean. Of course, we need axioms, right? So this is the structure. What does it satisfy? Well, a couple of things. All of them are kind of obvious things if you think about it, and I will comment on the axioms in a moment. First, we want additivity, which means, well, on the one hand, the empty groupoid has to go to the zero category, which is, I mean, the zero additive category. It's the final and initial additive category. And a disjoint union of groupoids goes to a direct sum of additive categories. And by direct sum, I mean the Cartesian product, which is both a product and a coproduct in add, okay? Nice exercise. So, all right, we have this. Then I want that every restriction functor, so this I upper star associated with every faithful morphism of groupoids, I wanted to admit a left adjoint and a right adjoint, which I call I lower shriek and I lower star, respectively. This is the notation from derivator theory. If don't complain with me, that's just a shorthand, so I don't have to write ind and co-ind all the time. Then what do I have? I want a left and a right base change formula, meaning that I have all these adjunctions, left adjunctions, right adjunctions. Well, they have to satisfy base change with respect to all iso comma squares of groupoids. So I will comment on that later. Let me give the last axiom. So if you look at these three axioms so far, they are just like three of the four axioms of additive derivators. They are equivalent to three of the four axioms of additive derivators. If you know about derivators, try to think about that. The fourth axiom replaces the one missing axiom of derivators and changes the whole theory, okay? So what is the fourth axiom? Is between the left and the right adjoints to the restriction along any morphism of groupoids, okay? This tells us that we're talking about, finite groups here. All right. Before commenting on each of the axioms and saying why it's there, let me tell you straight away that we can do variations. We can change the domain. So we have this is what I would call a global notion of Mackey to functor defined on all groupoids, but you have a local variant for some fixed G. So you have a group G, maybe you have structure which is only defined for the subgroups of G. So I will replace in that case my two category of groupoids with the comma two category over G, which this means you take groupoids which come together with a fixed embedding or faithful functor into G. And in fact, little exercise, this is bi-equivalent to the ordinary category of finite left G sets. Very nice. Kind of explains why G sets are used for Mackey functors classically, if you've encountered them. But I will just keep this axiomatization. There are many variants, but this is the main one. All right, so what about these axioms? Why do I want these? Well, first of all, this doesn't come out of the blue, but it's inspired by the theory of ordinary abelian group valued Mackey functors. This is a very old theory starting in the 60s with J.A. Green, Andreas Dress, Harald Lindner, many other people. It's the very first axiomatic representation theory. It's made in terms of Mackey functors. So what we do here is a categorification of Mackey functors in a specific way. Then we also have additive derivators, which, as I have hinted, have three of the axioms in common, and then one is different. And also, there are similar theories nowadays. Like there is a very closely related but somehow complementary theory due to Clark-Barwick, where his Mackey functors are infinity functors, or functors of infinity one categories. So we don't go all the way up. We are content with two categories, but we allow non-invertible two cells. So that's the difference. Okay, so that's kind of complementary here. All right. So let's explain why we want additivity. Well,
but sorry, just a quick question. Do you also have the Frobenius condition on the adjunctions on Barwick definition of making functor?
No, he doesn't have. No, it's hidden in the machine.
Oh, I lost your answer. You lagged for a second.
Sorry. So what he has, Barwick, he defines. For him, a Mackey functor is defined on some infinity category of spans and lands in some infinity category of spectra, whatever. So you cannot talk about adjunctions in the target. It's a different way of seeing things, but
I see.
So I could talk about the similarities and differences, but I mean, first I have to explain where spans come in, and I will.
Oh yeah. I see. Thank you.
But otherwise, many of the ideas are in common. Yeah, but he cannot talk about adjunctions as I do here. So, sorry, if there is a lag and you lose something, please let me know, because I tend to talk a bit too fast. So in a 2-second lag, you might miss a whole definition. So this first axiom says, well, first of all, you know that every groupoid decomposes up to equivalence into groups, right? You have to choose some object in each component, but then you have a bunch of groups. So the data of my two-functor n, thanks to this axiom, is determined by what it does on groups, on the two subcategory of finite groups, right? So these functors, which I had named a couple of slides ago, the restriction functors, the conjugation, well, I also had abstract isomorphism functors, because I don't only have conjugations between subgroups, but abstract isomorphisms now between groupoids. And then I have this conjugation two cells, which are exactly the natural transformations of homomorphisms between groups, right? So this data I had in this slide before determines the Mackey two-functor, thanks to the first axiom, even though now there are groupoids all around. So groupoids are there to beautify things, not to add information, okay? So what else? Well, just like for derivators or similar structures, in my axiom, I don't want induction to be part of the structure. I want it to exist as an adjoint functor, maybe adjoint on both sides, right? But it's not really part of the data, right? It will be a bit too much to carry around all the time. And then ambidexterity, the fourth axiom, says that, you know, there is some isomorphism between left and right adjoint, and it could. So when you check the axioms and examples, it's easy because any isomorphism will do. You don't have to verify that it satisfies something particular. So any category theories would say, all right, what are you doing, Ivo? This information has to be coherent somehow, right? I mean, you cannot just take any isomorphisms between left and right adjoints and then hope that they glue together nicely and do, you know, high category stuff. But luckily, there is a theorem which says that you can. So the first fact of this theory is that we call this the rectification theorem. So if you have these axioms, if you have a Mackey functor, so in particular axiom 4 holds, so there exists isomorphisms like that between left and right adjoint for every I. Then there exists some other uniquely determined canonical, very beautiful isomorphisms, which are compatible with the adjunctions in a very precise way. So I write here fully compatible with the given left and right adjunctions for every I. I will not spell out all the properties, but you have a long list of desiderata, and they are all true for these canonical maps, which are invertible as soon as there is some isomorphism. Okay, this happens sometimes when you're lucky in mathematics. If two things are isomorphic, then a certain specific canonical map between them is invertible. If it happens, you're very happy. So I will use always this canonical best possible identification of left and right adjoints, and I will call both functors induction. That's it. All right, so what about the remaining axiom, the third one? Well, that gives me the Maki formula. So base change gives me some canonical Maki formulas. So what does the axiom say in detail? Let's have a look. So every isocomma square gamma, so an isocomma square is like you have 4 morphisms of group points, and this guy here on top is a comma category, okay, in group points. And then the canonical cell here will be invertible because these are group points, and so all natural transformations are invertible. Then by using the two adjunctions, so by using the left adjoints, you can pull back and then use the left adjoint to go up, to push forward, or you can push forward and pull back, right? And the left mate of gamma gives you a map that goes down here. Or you can use the right adjoints, and then you get a mate of gamma inverse, it goes up. And the axiom requires precisely that both these mates are invertible, okay? And the beautiful thing that happens is that you can show, so the rectification theorem says that these canonical isomorphisms theta between the left and the right adjoints, which identify these with these, this with this, they actually match these two isomorphisms. One corresponds to the inverse of the other. And if you think about it, if you have ever seen base change formulas in algebraic geometry or wherever, you never have this. Like base change says, oh, a certain mate is invertible, and you have two canonical constructions and they give mutually inverse maps. So it's very nice. So the motivating example, of course, is as follows. You have two of G. You have the two inclusions, I, which sends K in G, J, which sends L in G. You construct the comma object, I over J. And then it's easy to see that this groupoid, I over J, almost never, but it's a groupoid which decomposes like that as a coproduct of these groups. All right. So when you apply M, the two functor M, guess what? You get the Maki formula, right? The one that is used all the time. But it's better because if you don't use this equivalence, you keep this groupoid, then this square is canonical. So the isocomma groupoid, and therefore the base change isomorphisms which come with it are canonical. There are no choices involved. While once you use this, and you write down the formula with this ugly choice of cosets, double cosets, then everything becomes, you have choices, and then if you do it twice, you have choices over choices, and then nobody can keep track of anything. All right, so these are the axioms, and it's already 3. So what can we do now? If you have axioms, you need 2 things, right? You need examples and you need theorems. So let's start maybe with the examples. Well, the good news is Mackey 2 functors are everywhere. Anytime you have finite groups in any kind of mathematics which act on stuff, you have Mackey 2 functors. I will try to convince you with this slide. So there is a Mackey 2 functor M for each of the following families of categories, and which depend on a group G. So abelian or triangulated, because I want to show you that these are categories that interest people where they want to compute invariance in their, they have some structure, some interest in each of these subjects. So in representation theory, we have the categories that we just saw at the beginning, right? We have the representation category. You can even take all infinite dimensional representations, big abelian category, the bounded derived category, the full unbounded derived category, the stable object category, and then there are many others. Each of them defines by varying G a Mackey-2 functor. Then you also have Mackey-2 functors in other subjects. So I call this linear representation theory because then you can represent finite groups on, say, spaces, right? So let's go to topology. Well, you can take M of G to be the homotopy category of G spectra, what is called the equivariant stable homotopy category of genuine G spectra. It's also triangulated, like the draft category here. That's where people study generalized equivariant cohomological theories for spaces. I will say no more about that probably, but it's an important category for people who do equivariant topology. Then we also have for people who do operator algebras or non-commutative geometry, we can take the equivariant Kasparov category or the E theory of Hickson and Kohn, where the objects are sister algebras. They can produce some, objects are sister algebras with an action of the group G, okay? And they form these triangulated categories where they want to compute their various theories. But also in more usual geometry, you can look at equivariant sheaves. So this is an example or a family of examples which are defined locally only for a fixed finite group G. So you fix G, you fix X, some locally ring space. So that could be a scheme or an analytic space, anything, equipped with a G action by morphisms of locally ring spaces. Then for every subgroup H, you can define this category M of H of H equivariant sheaves over X, over the structure sheaf of X. That's an abelian category, right? So it's basically, sorry?
Here you don't mean sheaves of sets, you mean sheaves of abelian groups.
Yes, sorry, thank you. Yes, I want an additive effect on abelian category. Yes, sheaves of abelian groups over the structure sheaf of rings, right? Yes, thank you. All my categories have to be at least additive. So the thing is, this is the correct notion of, it's some kind of derived notion of invariant bundle or sheaf, right? I will not define it, but you can think of them as being the correct notion of sheaf over the quotient stack of X by the action of H. And there are variants, like you can take the derived category of this abelian category, or you can limit to constructible sheaves or coherent sheaves if X is some Noetherian scheme, and so on and so forth. All of these give you Mackey-2 functors. So there are many, okay? All right. So done with the examples. Let's go back to the pleasant abstractions. What can we do with these axioms? So let's see, what can we prove with these axioms? I'm going to give you some proper applications which let's say that people before had not noticed, because what we have axiomatized here is stuff that has been used for decades, but I want to give you some things that hadn't been noticed before because people had not done this systematically. So I will talk about some monadicity result at first. First thing is, well, this canonical identifications theta that we have found between the left and the right adjoints, they satisfy many properties, and in particular, they make this ambijunction special Frobenius. If you don't know what it means, it's simply the fact that if you take the unit of the left adjunction for any morphism I of group points here, so the unit, you can then compose it with the co-unit of the other adjunction if you identify using theta in the middle. And then this composite turns out to be the identity of the identity functor of M of H. So in some sense, it says that some monad has a rotation of the monad has a bilinear section or something like that. So what you can do with that, well, a corollary is that there is some kind of the back monadicity criterion that applies here once this is true, this separability condition. And you obtain as a corollary very easily that if M takes values in idempotent complete categories, for example, abelian categories, then for every I, the right adjunction is monadic and the left adjunction is comonadic. So you have a monad and a comonad on the big category, M of G, and the M of H will be canonically equivalent to co-algebras over the comonad, but also algebras over the monad. Okay, so what this means is that, like, morally, you can always recover the smaller, so the category of the smaller group from the category of the big group, which is kind of intuitive, right? So you can always do it in this canonical way. And this has many applications I will not talk about, but it's a typical thing that maybe, you know, representation theorists hadn't noticed before, and they hadn't noticed this before the year 2015, I think. So, but it's kind of clear once you have these things in your hands. But this is kind of, you know, that maybe doesn't really interest representation theorists, really. So what can we do? Well, we have the motivic approach, meaning that, so maybe it's a big word, motivic, the universal approach. So let's maybe introduce some coefficients here. I would say that a Mackey-2 functor is k-linear over some commutative ring K if it takes values in k-linear additive categories and k-linear functors between them. So K, you know, if it's just Z in integers, then it's just additive categories and functors. But it could be a field, it could be any ring really. So now we have this notion. Well, there is a universal k-linear Mackey-2 functor by this theorem. So more precisely, there is a two category, which I call here mod K, let's say of k-linear Mackey-2 motives, just the name. Mackey-2 functor M has to factor uniquely. Even better, if you have one of these k-linear Mackey-2 functors, so it lands here in k-linear categories, well, it has to factor through this universal two functor, but the resulting factorization here, it's a k-linear two functor. So on each home, okay, you have home categories which are k-linear, it's also target, and this M hat here is just some k-linear two functor. And vice versa, any k-linear two functor here, if you precompose it with the universal guy here, gives you a Mackey-2 function. So if you know about ordinary Mackey functors, they can be defined as just additive functors which have abelian groups as values, which are defined on some category of spans, some motivic category of G sets. Well, it's the same thing here, but you know, one layer of complication more. So, all right, what can you do with this? Well, you can compute in this two category of motives because you have concrete models. So let's see what we can do. For example, you have a two-cell endomorphism ring for each one cell. So if you take the identity of G, let's say you have a group G, well, you send it to its corresponding motive, which I still call G. Then its identity one cell has an endomorphism ring, which is commutative by general nonsense. Well, if I apply to it this k-linear two functor, well, the ring goes to act on my category M of G, all right? So this is a universal commutative ring which acts on M of G for the group G, but for any k-linear Mackey functor M. For any k-linear Mackey-2 functor M, if I evaluate it at the group G, I'll get an additive category on which this ring acts, okay? So what is this ring? Well, what is this ring? We asked this question for like a year before we managed to compute it, but This two category of motifs has many models, and you can play them against each other. So you can use spans in groupoids, you can use bimodules of some kind, you can use string diagrams. Anyway, after a while, you manage to compute some stuff, and we compute this ring. So this is an example of a computation you can do. So this ring, the motivic endomorphism ring of a group G, of the identity of a group G, is precisely something that was already known, something which is called the crossed Burnside K algebra, due to Yoshida. So it works like this. It's just called B, C, K, or G, doesn't matter. So you have to extend scalars to your ring of coefficient K, but it's just the K0 of some braided monoidal category. So K0 of what? Well, the category is just finite G sets over the group G equipped with the conjugation action of itself, some comma category. And then you equip it with a certain tensor structure that comes from the multiplication of G. Easy, but I don't want to give it in detail. I prefer to tell you that this ring is very concrete. So concretely, it's a finite free K module generated by the G conjugacy classes of pairs HA, where H is some subgroup of G and A is some element of the centralizer of H in G. And then multiplication in this commutative ring is given by this ugly formula.
Ivo, can I ask you a question?
Yes.
So this category mod K, it was introduced in your book, or it was known also to Yoshida?
No, this was introduced in our book. At least we gave 2 models for it, and then we found another, and then we realized that, well, it is related to some work of Yoshida, but for example, by this theorem. But he didn't know about the whole, because this ring is a piece of that 2 category, right? Small piece, but there is a much more around it. So I think Yoshida has many variants of this cross-Bernstein K algebra, and we suspect that some of them also live in our motivic 2 category, but we haven't checked. I mean, these are computations, you have to do some work. But this is done now. So what you can do is, people have studied this ring since 1997, and depending on the base ring K, they also know what their idempotent elements are. So if you have a ring acting on a category, the primitive idempotents or the idempotent elements of this ring decompose the category as a Cartesian product. So let's apply this here in an example to see that this is useful. So it is well known that the usual Bernstein ring, so that the K0 ring of finite G sets, acts on the homotopy category of G spectra, simply because the Bernstein ring is the endomorphism ring of the sphere G spectrum in degree 0, and the sphere is a tensor unit for the smash product, and it acts on everything. So topologists have known for a long time that this ring acts on the category, and they use it to decompose the category additively. But now we have a bigger ring because we have this crossed Bernstein Z algebra, which is a bigger ring than the usual Bernstein ring, which also acts. And so you get a decomposition of the category where you have more pieces, more primitive idempotents of the ring. Like for Z, these are not known, unfortunately, but we know that there are more. And if you localize in various fields and so on, you can actually say what they are. But it gets complicated. But this is a concrete application, right? By the way, sorry, how much time do we have? I don't know when we started exactly.
You have more or less 5, maybe 6 minutes.
Oh, okay, perfect. I only have one result to present. So I wanted to show some real applications, right? So this is something new in topology, for example, that just sketched here. Huh? In fact, you can decompose additively the equivariance stable homotopy category using this ring that representation theorists had studied for completely different reasons. Now I'm going to talk about what my student has done in the last couple of years. So it goes back to a very classical thing. So if you know some group homology, you have probably encountered this formula. It's a very classical result, which links group cohomology with the fusion groups. So the fusion is, groups act on their elements and subgroups by conjugation. And if you fix a prime number, then you have, the Silo theorems, you have the p subgroups are conjugated. And this action, what happens to p subgroups, is called the p fusion. And it's an important piece of the structure of groups, finite groups. So suppose that we are in a positive characteristic, and, well, I forgot to say this is P. Let's take a field of characteristic P, dividing the order of the group G. Now the so-called stable elements formula of Cartan and Eilenberg says that the group cohomology of G with coefficients in K is actually reconstructed as the limit of the cohomology of its P subgroups, where you also take into consideration the restrictions and conjugations. So you can formulate this as being the limit over the P fusion category, where the objects are the P subgroups of G, and the morphisms are all the inclusion and conjugation maps between them. So when you apply cohomology, you have restriction maps between P subgroups and conjugation maps on cohomology. Now, you can also do everything inside a single silo P subgroups. This is how you see it usually, just a variation. Okay, so the P subgroups and the fusion conjugation action, they determine cohomology. Group cohomology is a very small piece of the derived category of the group algebra. So, namely, group cohomology is just, the extensions between the trivial representation and itself, right? It's just this created home here. So guess what the question is? Can you do something similar to this limit and reconstruct the whole derived category from the derived categories of the P subgroups of G? Maybe together with the restriction and conjugation functors, maybe the conjugation isomorphisms. So using the Mackey 2 functional structure. What do you think? Can you do it or not? So luckily, the answer is yes. So my student actually managed to finish his thesis. So it's a very nice answer, actually. And it works very generally. So I will give you the precise definition I want to have here. So we say that a Mackey 2 functor M is cohomological if this composite is equal to the index of H and G for every subgroup inclusion of H and G. So what is that? That is not the identity. It's not the same composite as before in the special Frobenius property. It's the other one. Because now we use first the unit of the right adjunction followed by the co-unit of the left adjunction. Theory could be anything. In many examples, it's the index, it's multiplication by the index. So if that's the case, if that is the case in your Mackey 2 functor, then you have a Cartan-Eilenberg formula, which goes as follows. It's a categorification, namely that suppose M is an idempotent complete and K linear Mackey 2 functor with K some field of characteristic P. And you suppose that M is cohomological in this technical sense. Then there is an equivalence between the category associated to G and a certain bilimit. So bilimit is just a pseudo limit, okay? The bi-categorical notion of limit of M of P with P. So this bilimit is taken among K-linear additive categories or just categories, it's the same thing, over what people call the P transporter to category. So let me say two words why this is interesting. So this transported to category is just a refinement of the fusion. So it quotients down to the fusion. It's a little bit more information. And in fact, if you know about the orbit category, it's bi-equivalent to the orbit category of these orbits, G mod P for P subgroups of G. So topologists have used that for a long time. And you can take a bilimit over that of the Mackey 2 functor, and it gives you back M of G. namely all those from representation theory that we have seen at the beginning. But there are more, namely, we also have equivariant sheaves over some, say, G variety X defined over the field K. You can take sheaves, the derived category of sheaves, whatever you want. And the previous examples, these ones, they are just the case where the variety is the point, is the spectrum of the field, with the trivial G action. So now we have a very general categorified Cartan-Eilenberg formula, which can be used in algebraic geometry, for example, too. Hence the smiley here. All right, I have talked for enough time. I think I will stop here and thank you all for your attention.
Thank you very much, Ivo.
Thank you.
We have a round of silent applause, so you cannot hear it, but people are cheering in their thumbs. And so I would say we can open the very briefly the question time, because you went a little bit over time and I didn't want to
apologies for that.
No worries. So if someone has questions, please join the stage and ask your question.
If no one has, maybe something, I just want to book your attention, because if you haven't tried to connect precisely Mackey functors and derivators, I might have a piece of an idea for what is the precise relation in terms of two adjunction between the two category of derivators and Mackey functors, maybe.
But I have a relation. I have a precise relationship.
So tell me, and I won't tell you if I was right or wrong.
All right. So if you have a derivator, let's say we find on all categories, let's say additive, so it lands in additive categories. Any additive derivator, in fact. Well, inside here you have a finite groupoid, right?
Yes.
So you can restrict it. Just restrict it. And so there is a theorem that says that if you restrict an additive derivator to groupoids, finite groupoids, so here I had faithful morphisms.
Okay.
Then it's a Mackey functor.
Always.
Always. You have to show the hard part is to show the ambidexterity, because all the other axioms are true by hypothesis, because you have a derivator, which is additive. So you have to show axiom 4, okay, that the left and right can extensions, but it's true. It's true. You can show that by recursion on the order of the finite group.
Nice. I would have said that wasn't true, but you can impose the Frobenius condition. Yeah. No, it
was a bit of a surprise, but it's true. It's you can see it concretely, because when you construct left and right can extensions. So I mean, what is the induction?
Mackey functors are just restrictions of additive derivators to finite groupoids. That's the upshot.
No. But there are many more. These are some of them.
Oh,
so examples of this are modules, this, or the derived category even. These come as examples because you have a derivator for just additive representations of G in K modules. These are obvious examples. But then you have, for example, this example, or even simpler, the stable module category cannot arise this way, because if you take the trivial group G, what is the value here? What is this category if the group is trivial? It's 0. Okay.
We lost you.
Mackey functor, which has non-zero values for many groups, which happens to have 0 value at the trivial group. So it cannot come this way. It's not the restriction of an additive derivative, for example. But there are many more. All the other examples I gave are not coming from KK theory, stable homotopy theory.
Yes,
they are genuine examples.
You were concerned about this many years ago. Yes, concerned, interested, problem. Yeah, I remember. Okay, thank you.
I still don't know what. So there should be a notion of equivariant derivative which gives rise to all the Mackey functors. I don't know what the definition should be precisely. Nobody, as far as I know.
So thank you, Fosco, for the question. In fact, I also would like to ask a question, but I think there is no time. And also Ivo's connection is a little bit dropping now. So thank you very much, Ivo. I think we should stop here. And now,
All right.
I think I will send you an email because I have a question, but there's no time for it. So
Sure.
Again, thank you very much for your talk, and thank the audience for joining. And now we